All right, so this is problem 3-9. So we have two infinite cylinders and they're nested inside of each other. So two infinitely long coaxial cylindrical surfaces. So they're just hollow cylinders with a radius of A and radius of B. B is larger than A, so it's on the outside. And they carry surface charge densities of PSA and PSB. So there's a surface charge density on A and a surface charge density on B. So due to these surface charge densities, we need to find E everywhere. So there are a couple of different regions where E is going to be different. So for R is less than A, we're going to have a different E field for R is in between A and B. So this is the R of our Gaussian surface that we pick, and our Gaussian surface is going to be a cylinder that's going to just wrap around one or both of these, depending on what region it's in. And then we need to find the third region for B is greater than, or for this R is larger than B. So outside, in between these two, and in the middle. Okay, so to do that, we're going to use Gauss's law. And to use Gauss's law, we need to solve for the charge enclosed first due to the surface charge density. So we're going to need ds for a cylinder, so the differential surface for a cylinder. So we got this from our cheat sheet up here. We got dsr, which means the surface that has the r hat vector perpendicular to it. So if we see the r hat vector, it's perpendicular to the surface of the cylinder, and this is the piece that we want. This will be included in the description below. I've used this cheat sheet in previous videos, but just for reference for this one as well. Okay, so let's get started. So for the first one, for r is less than a, what's the charge that's enclosed in that area? Well, for r is less than a, if we look at what's enclosed in here, we don't have anything. If we're trying to enclose something and we have to be less than a, where the surface charge density is, there's actually nothing in there. So we don't have any charge to enclose. So what our expression is going to look like is ds, another vector, 0 over E naught. And then that's going to simplify even further to where we have E dot ds is equal to 0. And then where we have this E, r is equal to 0 divided by the integral of ds, which is equal to 0. Okay, so for the first part, we just have 0. You can show that, or you could just write that it's equal to 0. I just kind of wanted to prove that out to you guys. Okay, so for the second part, we're looking in between the radius for A and B. So this is the region that we're looking at in between here, in between these two. So less than B, but greater than A, which means that the charge enclosed will include the surface charge for A. So let's go ahead and set that up. So we have Q enclosed is equal to PSA, right? And then we're looking at the ds for a cylinder, so we can take this guy here. But notice that for this, because we have an infinite cylinder, we're going to do a couple of things. We're going to just model dz as L, because it's going to cancel on both sides. It's going to be the same on the right side of the equation where we're solving for the Q enclosed, and it's going to be the same on the left side where we're solving for the Gaussian surface, because they will both have an infinite length. So for the sake of ease for this problem, we can just model it as L. Okay, and then in this case also our R is going to be equal to A, just because that's what it is for this surface. And we are trying to find the charge enclosed, so we're integrating over the charged surface. Okay, so we're basically going to be able to turn some of those into constants. So we're going to have PSA times A times L, and then we basically just have d phi from 0 to 2 pi. So we have d phi, and when we're dealing with a cylinder, this phi angle is around the z-axis, so around the z-axis. And when we have a full cylinder, that angle is going to be 2 pi. So phi is here, right? And a full revolution, 360 degrees, is 2 pi. Okay, so let's solve that out. So we're just going to end up with PSA times A times L times 2 pi. Okay, so that's going to be our enclosed charge for this section here. So Q enclosed is equal to that. Okay, so it's important to look at these so you know how to deal with like infinity in our problems. So we can just model it as some general L. Okay, So on this side, we're going to take our Q enclosed and we're going to plug it in over here. So we're going to plug it in, and then we're also going to plug in our DS. So we are going to swap our E. We have an ER, so E in the radial cylindrical direction, and then we have R, and then we have d phi and dz. And we're going to do the same thing for this dz here, and we're just going to model that dz as L because we have an infinite length, and we're just modeling it the same on both sides. Okay, so is equal to our Q enclosed over E naught, so 1 over E naught, and then multiplied by what we found up here, so PSA times A times L times 2 pi. Okay, right away, let's go ahead and, well, let's take 1 second before we simplify, and let's integrate with respect to phi, d phi. And again, this is also 0 to 2 pi just because it is a cylinder. For these Gaussian problems, you are just dealing with a lot of surfaces that have general bounds. So if you want to just plug in the surface area for a cylinder for some of these problems, it actually mathematically works out, but you need to make sure that you know what you're doing. So if you get comfortable with these, note that you don't actually have to do all of the integration steps, but you need to know where they come from, or if you are just trying to cancel some things, you'll get tripped up. Sorry, there's an L there. Okay, so we can go ahead and cancel out 2 pi L from both sides. Okay, and then we're going to divide the other side by that R. So we're going to have ER is equal to 1 over E naught times PSA times A, and then we're going to divide by R. So we're going to have 1 over R E naught times PSA multiplied by A. So that's our E fields over here. Okay, just in between A and B. And we're going to go ahead and check that answer, and that is correct. So now we're going to look at the area outside of B. So Gaussian R that's outside of this B. So we found a Gaussian R in between A and B, and we found a Gaussian R in between A. Now we're going to find it outside of both of these. So outside of both of them, we have 2 surface areas that are charged, that are enclosed. So we have this surface area and this surface area, and outside we're taking both of them into account. Okay, so by doing that, okay, we have PSA, oops, sorry, we have PSA times, and we're going to do the ds for each of these separately. So just as a recap, ds, R for a cylinder, is equal to R d phi dz. So we're doing the same thing where we're modeling this dz as just an L to deal with the infinite surface, and we're going to respectively do the radiuses for both of these. So, okay, so we're finding the integral here, PSA times the radius for PSA is A, right? Its respective radius, and then we have this L, right? And then we have d phi. Okay, and then we're going to add PSB multiplied by its radius, B, oops, its radius B, right, the respective radiuses of where those surfaces are at, right? I'm going to find it at B. And then multiplied by this L, because we decided to model it that way, and then d phi. Okay, so for d phi, it's going to be the same here. We're just dealing with a full cylinder, so 0 to 2 pi all the way around the z-axis. It's going to be the same throughout the problem. So it's the only differential element, so it's the only thing that we're going to have bounds for. So 0, I'll write that a little bit darker. So 0 to 2 pi, 0 to 2 pi, which means that our Q enclosed is going to be equal to PSA times A times L times 2 pi, right, plus PSB times B times L times 2 pi, right, and we can go ahead and simplify that, equals 2 pi L, because it's multiplied by both, right, PSA times A plus PSB times B. Okay, so we found our enclosed charge for that area, right? Okay, now we are going to plug this in to our Gauss's law equation and solve for this part. So same thing on the other side here. We have our radial E fields. multiplied by r, and then d phi dz, and we're multiplying or we're modeling our dz as L because we have an infinite length, right? Because this cylinder is infinite. It's going to infinity on both sides, so this z is infinite. So we're just going to model it as some length L, okay? D phi times L. Okay, and we'll keep the integral on the outside here. And then our d phi again is 0 to 2 pi because we have a full cylinder, so this is common, you know, for all of these, because we have very similar shapes. Usually a Gaussian shape will go around, well, not usually, but often a Gaussian shape will go around a very similar shape. Okay, so PSA times A, PSA times B, and so this is our Q enclosed, right? And multiplied by 1 over E naught. So we have our Q enclosed on this side. So we got it from here and plugged it into here. Okay, so that's where we're at so far with our expression. Okay, so let's simplify this guy a little bit more. So we can put our ER times R times L, and then d phi is going to just turn into 2 pi, okay? And 1 over E naught times 2 pi L times PSA times A plus PSB times B. Okay, so we can cancel this 2 pi L because we have it on both sides. So 2 pi L can cancel, 2 pi L can cancel. Okay, oh, let me keep this green here so we know that this is the variable R for our Gaussian surface because that moves. So we're just trying to get an expression for R. So that's the R that we're changing. Okay, so then we're going to divide by R. So we have R, okay, 1 over R times E naught times PSA times A plus PSB times B. And let's go ahead and check that. And that is correct. Okay, so that's our E field for that section as well. Okay, so we just solved for our E field in the 3 regions, just to recap. So we found our E field to be 0 inside of here because there's no enclosed charge. For our surface in between A and B, we found our E field just to be due to the surface charge of A, and then outside of B, we found the E field to be due to the surface charge of A and B. Now we're going to do part